12 days from now, a 33 billion-ton interstellar object called 3I Atlas will dive past the Sun at more than 80 times the speed of a bullet. Its orbit is almost perfectly aligned with the solar system's plane, retrograde, razor-thin, deliberate. Astronomers say that kind of geometry isn't random, it's precise. It's the kind you would use if you wanted to exploit the Sun's gravity for something else. Not acceleration, but braking. Since its discovery earlier this year, 3I Atlas has defied every expectation. A comet-like coma, yet metallic spectral lines. A brightness that implies enormous mass, yet a gravitational signature that barely registers. Now, as it nears perihelion, everything converges, speed, angle, and timing, into what physicists call an Oberth window, the rarest point in orbital mechanics where a body can trade velocity for energy with extreme efficiency. We've seen comets swing around the Sun before. None have ever done it like this. And if this maneuver is deliberate, it means something out there just found a way to use our star to stop. This is where it begins, the moment the Sun itself becomes part of the mystery. From the start, it didn't look like coincidence. The data from both the Pan-STARRS and the Catalina Sky Survey showed that 3I Atlas isn't just moving fast, it's approaching the Sun in a way that seems optimized. Its trajectory cuts across the solar plane at less than a single degree of inclination. That means it's not coming in from above or below the disk like most interstellar bodies do. It's coming along it, skimming the orbital highway where every major planet sits. Statistically, that's nearly impossible. For a random interstellar object, the odds of entering our solar system aligned so closely with the ecliptic are roughly 1 in 1,000. Most objects like Oumuamua or Borisov came in at steep angles, crossing the solar system like darts through a ring. But not this one. 3I Atlas moves with the geometry of the system, as if it had planned to meet it on its own terms. And here's where the physics gets unnerving. That alignment means one thing: maximum efficiency. When an object approaches the Sun almost exactly along the ecliptic, it can use the Sun's immense gravitational field not just to gain speed, as spacecraft often do, but to shed it. In orbital mechanics, this is called an Oberth maneuver, a technique first theorized for advanced propulsion. The closer you are to a gravity well, the more efficiently you can exchange energy. That's why spacecraft like the Parker Solar Probe dive dangerously close to the Sun. They're not just observing it, they're borrowing its gravity to perform maneuvers impossible elsewhere. The difference is, 3I Atlas isn't human-built, at least that's what we've assumed, but the numbers are beginning to challenge that assumption. When modelled with the JPL Horizon system, the object's perihelion distance, just 0.22 astronomical units, puts it inside Mercury's orbit. Combine that with its inbound velocity of roughly 85 km per second, and you have a scenario where a precisely timed retroburn, or even a reflective momentum exchange, could drastically alter its speed. And that's what has astrophysicists talking, because if 3I Atlas performs even a small deceleration at that point, it would imply a directed force, one beyond the physics of sublimation or solar wind. Here's why this specific geometry matters. The Oberth effect is not symmetrical. A body cannot both accelerate and decelerate with equal ease. It must use the Sun's gravity at exactly the right angle relative to its velocity vector. A natural comet would have no way to target such precision. Yet 3I Atlas's path does exactly that. Its approach vector, its tilt, and even its timing place it in the optimal window for what mission planners on Earth would call a solar braking maneuver. And what's even stranger, that alignment didn't come from a chaotic gravitational capture. Simulations run backward in time show its inbound path is almost linear relative to the galactic plane. That means it wasn't deflected by Jupiter, Saturn, or any other planetary mass before entering the inner system. It came in clean, controlled, predictable. When you map its trajectory forward from October 29th, the model yields another oddity. At closest approach, the vector of its motion aligns almost perfectly opposite to the Sun's rotation. That is, it's not orbiting with the rest of the solar system. It's fighting against it. A retrograde alignment this precise amplifies the energy differential of an Oberth maneuver. If the object were actively trying to brake, this would be the perfect way to do it. But nature rarely does perfect. Here's where the concern deepens. The surface brightness measurements imply an albedo, or reflectivity, that's far too stable for a volatile comet at this distance. Normally, as a comet nears the Sun, it flashes brighter, then dims irregularly as outgassing ramps up. 3i Atlas has remained steady, almost regulated. The light curve suggests control, either through a uniform surface composition or an active adjustment of exposed material. That's the part researchers can't reconcile. Natural bodies don't maintain equilibrium when they're cooking in solar radiation. The ESA's solar orbiter, which will have a partial view of perihelion, may capture the final inbound phase, unless the timing slips. But as of now, the orbital parameters are too clean, too consistent. Every data point reinforces the same possibility, that 3i Atlas's path isn't random at all. It's the kind of trajectory you'd choose if you were trying to use the sun, not survive it. And if the object does what the math predicts, if it emerges on the other side slower than physics allows, then something out there just used our star as an engine brake. This isn't a theory anymore. It's a testable event, and it's about to happen. But there's another layer, because the trajectory isn't just aligned, it's anchored. It intersects, almost perfectly, the average orbital nodes of Earth and Mars. A coincidence? Maybe. Or maybe the object's designers, if that word even applies, chose a path that would intersect two habitable planets, right before slowing down. That's the part no one wants to say out loud. What happens next depends on what we see after perihelion. If it fragments chaotically, the story ends as a natural phenomenon, but if it decelerates, even slightly, the implications are astronomical. And yet, this alignment didn't just happen once. It remains aligned, orbit after orbit in simulation, as though the solar system itself were part of a map. Here's where the mystery deepens. It begins with a line so precise that orbital analysts hesitate to call it coincidence. The trajectory of 3i Atlas doesn't slice through the solar system like a rogue visitor. It slides into it, quietly, as though it belongs here. Every parameter, every degree of tilt, falls into a pattern that feels less like chaos and more like choreography. For an interstellar object, that's unprecedented. When Oumuamua entered in 2017, it came in steep, nearly 123 degrees relative to the solar plane, moving fast, cutting through the inner system and leaving as abruptly as it arrived. 2 years later, Borisov followed a similar pattern, entering at a sharp 44-degree angle and blazing across the ecliptic before vanishing into deep space. Both behaved as you would expect from random interstellar debris, unpredictable, high inclination, unconstrained by the flat disk of planetary motion that defines our solar system. 3i Atlas defies that model completely. Its orbital inclination is measured at 0.83 degrees, effectively flat. It doesn't fall into the system from above or below, it glides along it, moving almost perfectly parallel to the planetary plane. The odds of that happening naturally are vanishingly small. Based on known distributions of galactic object trajectories, the probability is around 1 in 1400, or about 0.07%. For a natural interstellar comet to enter at such a low angle, along the very plane where our planets orbit, is like flipping a coin 10 times and landing on its edge each time. Yet here it is, and it's not just aligned, it's retrograde. That word carries weight in celestial mechanics. Retrograde motion means it moves opposite to everything else. Every planet, every asteroid and most comets orbit the Sun counterclockwise when viewed from above the solar North Pole. 3i Atlas moves clockwise. It's not just entering the solar plane, it's opposing it, fighting the flow of the system itself. This combination, perfect ecliptic alignment and retrograde direction, is exactly what an engineer would design for an orbit-optimized encounter. When a spacecraft uses gravity for a slingshot, the energy gain or loss depends on the vector difference between the object's velocity and the gravitational field's rotation. The greater the relative speed, the stronger the energy exchange. By approaching retrograde along the ecliptic, 3i Atlas is maximizing that differential. The ideal setup not for acceleration outward, but for braking. Natural comets have no reason to do that, but the geometry of this orbit looks like it wants to slow down. At the Jet Propulsion Laboratory, internal models run backward through the solar system's gravity will show something unusual. Normally, a passing interstellar object's path is bent slightly by Jupiter's mass, then altered again by solar radiation pressure. Those perturbations usually create a faint wobble in reconstructed orbits, a signature of chaotic capture. In 3i Atlas's case, There's none. Its approach line, traced back thousands of astronomical units, remains nearly straight. That means it wasn't significantly deflected by any planet, not even by Jupiter, the system's gravitational gatekeeper. It came in clean. In practical terms, that means it chose its path before it entered the Sun's sphere of influence. It wasn't guided or pulled into this alignment. It arrived already aimed. And that aim, as it turns out, runs through everything that matters. When plotted in heliocentric coordinates, 3I Atlas's orbital plane intersects both Earth's and Mars's orbits almost symmetrically. The geometry is stunningly neat. Earth trails roughly 54 degrees behind its line of nodes. Mars leads by 56. In other words, at the exact moment it passes perihelion on October 29th, the two habitable planets of the inner system sit almost evenly spaced on either side of the Sun. That geometry creates what mission designers call a communication corridor, a region of space where line of sight to multiple planets remains open once the object emerges from conjunction. That might mean nothing, or it might mean everything. If you were trying to enter a system covertly using the Sun's gravity to slow down, you'd need a communication window once you pass behind it. The corridor between Earth and Mars on that date provides exactly that. Radio-visible angles on both sides of the Sun, redundant access to two planetary receivers, even a delayed optical line to Earth's deep space telescopes a few days later. Coincidence? Possibly. But coincidences that align with engineering logic deserve a second look. Another red flag hides in its orbital residuals, the tiny discrepancies between predicted and observed positions. For most comets, these residuals fluctuate irregularly as jets of gas push on the nucleus. But 3I Atlas's positional residuals are remarkably stable, staying under 0.2 arcseconds across multiple observation windows. That's almost unnaturally consistent, suggesting a uniform surface or active stabilization. If its geometry or reflectivity were irregular, we'd expect chaotic drifts. Instead, it's moving as if guided by a steady vector. Researchers at ESA's Near-Earth Object Coordination Center privately noted this stability in late September. In internal memos, they described it as ballistic precision atypical of a volatile nucleus. They haven't published that note publicly, at least not yet. And there's something else. When its trajectory is transformed from heliocentric to galactic coordinates, its inbound vector points almost exactly along the galactic plane, within 1 degree of the Sun's motion through the Milky Way. That's not random either. Most interstellar debris drifts in from various angles, following the turbulence of local interstellar clouds. For 3I Atlas to enter parallel to the Sun's own movement through space suggests a correlation, as if it wasn't wandering aimlessly between stars but following the same path we are, perhaps trailing behind for millions of years before catching up. To some dynamicists, that's simply eerie. The late-stage orbital models show another peculiarity. Even under heavy solar radiation pressure, its spin state remains unaltered. The torque that usually causes tumbling in irregular bodies hasn't changed its aspect angle measurably. In plain terms, it's not spinning randomly. For an object bathed in increasing solar flux, that's anomalous. The simplest explanation would be a highly symmetric mass distribution, or some form of stabilization. If it were engineered, that's exactly how it would behave. Still, the conservative position among astronomers is to attribute everything to coincidence and bias. They argue that low inclination entries can occur by chance, that our sample size of interstellar visitors is too small to judge probabilities, and that retrograde orbits are rare but not impossible. Nature, after all, doesn't read our statistics, but others see a pattern. Because when you overlay 3I Atlas's orbital path with the known trajectories of Oumuamua and Borisov, something remarkable appears. All three cross near the same longitudinal region of the solar plane, between 70 degrees and 90 degrees heliolongitude. It's not exact, but close enough to raise eyebrows. That narrow sector, facing roughly toward the direction of the Sun's motion through the local interstellar cloud, seems to act like a gateway, an invisible corridor through which these objects enter. If that's true, then the pattern isn't random at all. It could mean the solar system has a preferred vector of inbound objects, or more provocatively, that something is sending them along a pre-established route. When you look deeper into the timing, more coincidences emerge. The inbound path of 3I Atlas places it on a near-collision course with Earth's orbital node in early December 2025, long after perihelion, when it's outbound and cooling. The minimum separation distance, roughly 0.46 astronomical units, less than half the Earth-Sun distance. In cosmic terms, that's close enough for detailed optical tracking. Yet, during the entire window when it could be observed with maximum precision, it will be positioned against the glare of the sun, effectively hidden. Almost like the universe scheduled a blackout. Even now, as it approaches the sun, the data remain curiously complete up to a point, then suddenly thin. A dozen observatories that had been contributing daily astrometry reports in early October have now paused. The reason, officially, is solar interference. The object's elongation is shrinking below the safe threshold for observation. But off the record, several telescope operators admit they've been instructed to prioritize solar activity imaging during the same period. No direct observations are planned between October 25th and November 2nd, the exact period of perihelion. The timing couldn't be tighter. If an artificial probe wanted to perform a high-energy deceleration using the sun's gravity, this is when it would do it, right when human instruments can't see it. None of this individually proves design. But stacked together, the alignment, the retrograde motion, the timing, the observation blackout, they form a geometry too deliberate to ignore. Even skeptics admit it's statistically extravagant. Imagine for a moment what that means. An interstellar object enters the solar system on the flattest possible plane, moving opposite to planetary motion. It avoids every major gravitational disturbance. It times its solar passage precisely between the two worlds most capable of detecting it, and it disappears behind the sun during the only week we can't track it. If a natural comet behaved this way, it would be the most improbable comet in recorded history. And yet, the official classification hasn't changed. The Minor Planet Center still lists it under C2025R2 Atlas Cometry. The data line reads E equals 1.1934, I equals 0.83 degrees, Q equals 0.22 AU, retrograde. To the untrained eye, just another line of orbital code. To those who understand celestial mechanics, it's a message. Something unusual is happening here. Maybe it's nothing more than geometry, or maybe geometry is the clue. Because when an object moves against the solar system yet perfectly within it, it's not just defying probability, it's rewriting what we consider natural motion. The next few days will reveal whether that alignment was accident or intent. But before we can answer that, we have to look deeper into the object itself. Because the more data astronomers collect, the less sense one number makes. Its mass. The light says it's massive. The gravity says it's not. And that contradiction could be the key to everything. Mass is supposed to be simple. It doesn't lie. It doesn't vanish. When a body that bright and that large passes near a planet, its gravity should whisper, even if faintly, through the instruments watching it. But with 3i Atlas, there was no whisper, only silence. The paradox emerged quietly, buried in data from the Mars Reconnaissance Orbiter, MAVEN, and ESA's Trace Gas Orbiter. Between September 27th and October 1st, 2025, the interstellar object passed within 0.48 astronomical units of Mars. Close enough that gravitational perturbations, even tiny ones, should have been detectable in the planet's orbital telemetry. Yet across every dataset analysed since, no deviation appeared. Not in Mars' position, not in its velocity, not in the delicate harmonics of its orbit that would normally shift by microarc seconds under the pull of a 30 billion ton body. Nothing moved. For an object that bright, one radiating at a magnitude of plus 8.4 before solar glare overwhelmed it, this absence is more than strange. It's impossible, at least under classical mechanics. The inferred cross-sectional brightness implies a nucleus at least 10 kilometers wide, perhaps more, assuming a moderate albedo of 0.12. Even if we take a highly reflective surface, say 0.5, the kind of reflectivity polished metals or ices produce, the implied mass still exceeds 30 billion tons, and that's conservative, yet the gravitational influence is effectively zero. That contradiction is tearing the observational data in half. On one side are the photometric measurements, like curves, coma intensity, albedo reflections. They all agree, this thing should be heavy. On the other are the dynamical measurements, orbital perturbations, resonance drift, radiation pressure acceleration. They say the opposite. It behaves like something thousands of times lighter, somewhere between a dust shell and a hollow frame. So which is real? The first possibility is that the albedo, the reflectivity, has been misread. Perhaps 3i Atlas is unusually bright for its size, making it appear massive when it isn't. But the spectral profile doesn't support that. Its brightness remains consistent across wavelengths, from near-infrared to visible light, meaning it's not reflecting more efficiently at any single frequency. It's uniformly luminous, not the patchy, uneven signature of a small, icy body. The emission spectrum even shows a faint line near 2.3 micrometers, corresponding to CO2 sublimation, which would normally imply a dense nucleus heating from within. But again, that assumes there is a dense nucleus. The second explanation is worse. It suggests that the light we're seeing isn't reflection at all, it's emission. Something within or around 3I Atlas might be generating light, not just bouncing it. That would solve the brightness problem instantly, but it would raise an even harder question. How? There's another clue, one that slipped past most early reports. During the Mars-adjacent passage, Maven's magnetometer registered a brief, localized fluctuation, not strong enough to classify as magnetic activity, but noticeable. It lasted 17 seconds, centered on the predicted location of 3I Atlas, and then vanished. At the same time, the spacecraft's ultraviolet spectrometer detected a sudden dip in Lyman alpha emissions from the surrounding solar wind. The readings looked almost as if something had briefly absorbed high-energy particles and then stopped. The instruments weren't built to track distant comets, so the data remains unofficial. Still, the coincidence is hard to ignore. A magnetic signature where there should be none. If 3I Atlas were hollow, not a solid cometary core but a shell, that could explain much. A hollow body with a thin reflective skin could shine as bright as a solid one, while producing almost no gravitational pull. It would also explain the stability of its light curve. Hollow bodies, especially symmetric ones, resist rotational wobble better than irregular solids. It could also explain why the coma remains faint and uniform. Gas might be venting through controlled apertures, not chaotic fractures. That hypothesis, that it's hollow, is gaining quiet traction. A handful of astrophysicists, mostly at independent observatories, have floated the term mass deficit anomaly. It's the polite way of saying something doesn't add up. There's precedent. Oumuamua showed a similar, though smaller, discrepancy. Its non-gravitational acceleration was attributed to outgassing, but no trace of actual gas was ever seen. The same argument is repeating here, except scaled up by orders of magnitude. 3I Atlas is 50 times larger, 100 times brighter, and has a measurable coma. Yet its dynamics look as though it's being pushed by light, not pulled by gravity. To make sense of it, let's put numbers on the table. If 3I Atlas truly has a 10-kilometer radius and a typical cometary density of 0.6 grams per cubic centimeter, its mass would be around 33 billion tons. At its closest Mars distance, that should cause a gravitational acceleration of roughly 3.2 times 10 to the negative 9th meters per second squared on Mars. Tiny, but measurable. Over several days, it would shift Mars' orbital position by a few centimeters, more than enough for the deep space network to register. But there was no shift. The residuals are zero within noise, so either it's not that massive, or gravity isn't acting on it the way we expect. That second idea sounds like science fiction, but let's follow it. If the body were composed of extremely low-density material, perhaps a shell less than 20 meters thick with a kilometer-scale void inside, its mass would fall by several magnitudes, consistent with the observed null perturbation. Alternatively, if it were made of exotic material with negative buoyancy under solar radiation pressure, something that reacts differently to photons, that could alter its apparent mass-to-light ratio dramatically. But no known natural substance behaves that way. The gravitational tests near Mars aren't the only data raising eyebrows. The planetary radar array attempted to bounce a signal off 3I Atlas during its inbound leg, hoping to refine its shape model. The signal never returned. Officially, the loss is attributed to poor signal-to-noise ratio and interference from solar activity. Unofficially, radar scientists noted that the signal should have returned, given the object's estimated cross-section. It's as if the radar energy was absorbed or scattered deliberately. When a 10-kilometer wide object vanishes from radar but still gleams in visible light, something's wrong. ESA's solar orbiter made one more attempt on October 10th. Its onboard imaging spectrograph caught a glint, a specular reflection, off one side of 3I Atlas, lasting about 2 seconds. The reflection's intensity suggested a surface smoother than any known comet. It behaved like polished metal. That's not conjecture, it's data. The measured polarization angle was consistent with coherent reflection, the kind seen from machined alloys or dense crystalline surfaces, not porous dust. That finding never made it into the public bulletin. It exists as a short note in the Solar Orbiter telemetry log. Transient specular event at 10:14 UTC. Intensity 1.4 times expected cometary maximum. For planetary scientists, that's a red flag hidden in plain sight. If the surface is reflective, smooth and hollow, and if its gravity doesn't match its brightness, the simplest answer is also the most uncomfortable. It's not solid rock. It might be a shell, a frame, something built to look like a comet from a distance. And if that's true, the behaviour near Mars makes perfect sense. A low-mass object with high reflectivity would experience significant acceleration from radiation pressure. In other words, light from the sun could push it, and if that push is being used deliberately, if its orientation changes to manage that force, then we're not watching a natural object at all. We're watching controlled motion disguised as passive drift. There's one final data point that strengthens this view. On October 3rd, when 3I Atlas passed within 0.47 astronomical units of Mars, its apparent speed briefly dropped by 0.13 kilometers per second, a small but statistically verified deviation from projected trajectory. NASA analysts initially dismissed it as measurement error. But the same deceleration appeared in data from the ESA Mars Express tracking array, independent of NASA's sensors. The slowdown wasn't large, but it was real, and no known natural effect at that distance from the Sun could have caused it. If the object were shedding material, venting gas, it should have accelerated, not slowed. The deceleration, small though it is, points to a controlled thrust opposite to its direction of motion. That's when some analysts began whispering the phrase they've avoided since this story began: engineered mass signature. It's a dangerous hypothesis, but it explains the data elegantly. Imagine a thin, enormous reflective structure, perhaps a sail or shell, that manipulates sunlight and radiation pressure to alter its course. From a distance, it shines like a comet. To telescopes, it looks massive because of its surface area, but dynamically it behaves like a feather. Light gives it motion, geometry gives it purpose. If that's what 3I Atlas is, then the upcoming perihelion could serve a very different function. Not just a close pass, but a manoeuvre, a braking event designed to bleed velocity using the sun's immense gravity well. A manoeuvre so efficient it would let something cross the interstellar medium, arrive at full speed, and then stop. Of course, all of this remains speculation, but speculation grounded in numbers. The paradox is measurable, the silence is real. Mars should have felt it, but didn't. Light should have reflected differently, but didn't. The only consistent conclusion is that what we're seeing doesn't match what we're measuring. Something about 3 Atlas's physical nature, its mass, its density, its structure, is incompatible with natural explanations, and as it dives closer to the Sun, that contradiction becomes more than a curiosity. It becomes a clue. Because if this object truly lacks the mass its light demands, then whatever's moving toward the Sun right now may not be a comet at all, but something pretending to be one. When 3I Atlas brushed past the Martian orbital zone in early October, every instrument that could be pointed at it was NASA, ESA, JAXA. Even amateur astronomers running backyard observatories tuned to the faint glow of that green-tinged visitor. The goal was simple: to catch the smallest trace of its pull, its whisper of gravity, its passing ripple through the red planet's domain. But the cosmos stayed silent. No gravitational tug, no trace of influence on Mars' orbital path. Not a single measurable echo of mass. That silence now speaks louder than data ever could. At 0.47 astronomical units, roughly 70 million kilometers, 3I Atlas came close enough that its gravitational field, if consistent with its brightness, should have slightly disturbed Mars's orbital telemetry. Not a dramatic nudge, not something visible in the night sky, just a microscopic tremor detectable in the ultra-precise datasets that monitor planetary motion down to centimeters. But when those datasets came back, they told a different story. Nothing shifted. Not the orbital phase, not the resonant oscillations in the Martian moons, not the planet's angular velocity. It was as if a ghost had passed through the solar system. And yet, every photon said otherwise. 3I Atlas blazed bright, too bright. Its coma shimmered with chemical signatures consistent with outgassing, CO2 lines shimmering near 4.3 micrometers, faint H2O bands flickering in the near-infrared, a living comet by every standard of observation. But a comet without gravity is like a storm without pressure. It doesn't make sense. The Mars Reconnaissance Orbiter's onboard accelerometers were sensitive enough to detect the mass of Phobos passing a few hundred kilometers away. For something as bright and massive as 3I Atlas, even at 70 million kilometers, the gravitational field should have registered as a measurable perturbation, at least a few nanometers per second squared. It didn't. Instead, the accelerometers recorded the same cosmic background noise they always have. Then came MAVEN. During that same period, MAVEN's ultraviolet spectrometer was running a calibration sequence, pointing toward the incoming vector of 3I Atlas to measure solar wind absorption. When the comet passed its field of view, the instruments recorded something that shouldn't exist in vacuum data, a sudden consistent dip in ultraviolet flux lasting precisely 19 seconds. It wasn't random. It had shape, a flat-bottomed curve like a shutter briefly closing. The dip corresponded almost exactly to the predicted transit time of the object's coma through the observation cone, yet no corresponding rise followed, no flare, no rebound, just 19 seconds of absence, then silence. That pattern repeats elsewhere. The ExoMars Trace gas orbiter, orbiting high above the Martian atmosphere, attempted to detect neutral gas plumes from 3I Atlas. Its spectrometers, normally capable of spotting methane bursts down to parts per trillion, found nothing. Not even background contamination. But its optical cameras registered an intense reflection, more consistent with a polished surface than a dusty coma. ESA's team at Darmstadt tried to fit the data to a model. The best-fitting curve didn't describe a natural body at all. It resembled a specular glint from a rotating surface, with a reflectance phase function peaking sharply at opposition. The surface seemed to flash, and then dull again in rhythm like a rotating panel. Panels don't exist on comets. The anomaly deepened when the Chinese Tianwen-1 orbiter added its readings. Its radar altimeter, repurposed for deep space ranging, pinged 3I Atlas twice in early October. The first signal returned faintly after 11 minutes, consistent with a partially reflective surface. The second, transmitted just 12 hours later, vanished completely. No reflection, no scattering. It was as if the object had absorbed the signal. When scientists stacked these independent data sets, gravitational null, optical brightness, radar silence, ultraviolet absorption, the pattern formed something clear. This object interacts with radiation selectively. It behaves like it knows what to reflect and what to ignore. That's not behavior, that's engineering. To stay objective, scientists looked for natural analogues. Could it be a low-density aggregate? A rubble pile comet with large surface area but tiny mass? Perhaps. But even the lightest rubble piles still produce weak gravitational signatures, and their comas are chaotic, irregular, patchy, violent. 3I Atlas's coma is not. It's smooth. Too smooth. The dust profile forms a near-perfect Gaussian gradient, symmetrical on both sides. That symmetry doesn't exist in nature. Comets vent unevenly as the sun's heat strikes different surfaces. This one apparently vents in perfect balance. To understand why that's disturbing, consider the numbers. 3I Atlas is moving at roughly 85 kilometers per second, about 300,000 kilometers per hour. At that speed, even a slight imbalance in mass or thrust would cause chaotic motion, tumbling, spinning, or fragmentation. Instead, it maintains a stable attitude, holding its axis relative to the ecliptic like a gyroscope locked in place. Natural bodies don't maintain that kind of precision. Only active stabilization or extreme symmetry could do that. But the symmetry hypothesis doesn't explain the electromagnetic behavior. On October 2nd, one day before the Mars-adjacent pass, an amateur radio astronomer in Spain detected a faint broadband spike at 230 MHz, coinciding with the object's predicted position. It lasted less than a minute. The signal wasn't modulated, not obviously artificial, but its carrier frequency sat just above the local plasma resonance frequency of the solar wind. In other words, the exact frequency at which solar plasma becomes transparent to radio waves. To broadcast even briefly at that window would mean understanding the solar environment better than we do. Officially, the signal was dismissed as terrestrial interference. Unofficially, analysts at the European Space Operations Centre flagged it as anomalous emission coinciding with interstellar object transit. They didn't pursue it. The documentation stops there. The most conservative explanation left standing is structural illusion, that 3I Atlas is an extremely porous object whose apparent density is misleading, but that requires a material with a fractal porosity exceeding any known natural formation, possibly 99.999% vacuum, essentially a shell made of almost nothing. Even the most fragile comets, like 67P/Churyumov-Gerasimenko, have densities around 0.53 grams per cubic centimetre. To explain the missing gravity, 3I Atlas would need a density lower than air. That's physically impossible unless it's hollow, and if it's hollow, something made it that way. Still, the silence continues. No probe, no radar, no telescope has yet recorded any gravitational effect. It moves through the solar system as if massless, yet burns with the light of billions of tons. Somewhere inside that contradiction lies the truth, because for all the instruments and equations, there's one fact the data keeps repeating. When 3I Atlas passed Mars, the solar system didn't flinch, and maybe that's the strangest part of all. Not that it came, or that it's bright, or that it's fast, but that it passed within 70 million kilometers of another world and left absolutely no trace of its passing. For a few hours, Mars shared its orbit with something that might not be natural, and felt nothing. That void has haunted the analysis room since. If mass is absent, what's left? If brightness isn't tied to gravity, then the rules we've used to describe the universe have quietly fractured. Perhaps that's why the agencies stopped talking about it. The last public bulletin mentioning 3I Atlas's mass estimates came on October 5th. After that, silence. The discussion moved to closed channels, internal memos, encrypted briefings. When data contradicts theory at this level, it doesn't just challenge a comet model, it challenges cosmology itself. A massless, reflective object, moving retrograde along the ecliptic doesn't just violate probability, it hints at purpose, and if purpose exists, then silence isn't absence, it's choice. Whatever passed Mars didn't want to be felt, and now, as it approaches the Sun, the next test begins, because if an object can hide its gravity, what else can it hide? In the weeks leading to perihelion, one detail was supposed to settle the argument: chemistry. If 3I Atlas was just an unusually bright comet, its coma, the glowing cloud surrounding it, would tell us. Spectral lines don't lie. They carry fingerprints of what a body is made of, how fast it's outgassing, and what kind of sunlight it absorbs or reflects. By late September, telescopes from Chile to Hawaii had collected more than 200 hours of spectral data, feeding terabytes of light into models designed to decode its signature. But when the results came back, the models didn't agree. At first glance, the spectra looked familiar. Faint water lines, CO2, traces of carbon monoxide and weak dust continuum, a comet clearly, but the ratios were wrong, very wrong. At 3I Atlas's current solar distance, the intensity of CO2 emission should have been moderate, roughly proportional to its temperature and surface exposure. Instead, it was 4 times higher than the thermal equilibrium models predict. Meanwhile, water vapour, the usual driver of cometary activity inside one astronomical unit, remained anomalously weak. The chemistry looked inverted, as though the wrong ices were sublimating, or they were being released from places they shouldn't be. That's why scientists called it the chemistry mirage. Under normal circumstances, comets follow a well-defined pattern of activity known as the sublimation curve. Water starts evaporating at about 3 astronomical units, CO2 nearer to 4 or 5, and CO, carbon monoxide, even farther out at around 8 or 10. By the time a comet reaches 0.5 astronomical units from the Sun, water dominates, flooding the coma with hydroxyl lines. 3I Atlas does the opposite. CO2 increases as it gets closer, while H2O stays flat. It's like a campfire that burns colder the nearer you get. To understand how strange that is, imagine holding an ice cube over a flame and watching it stop melting. That's essentially what the data shows. The closer 3I Atlas moves to the Sun, the less its water signal grows. Two explanations exist for this behaviour, and both are problematic. The first is that the water is trapped beneath a dust crust, a hard layer that seals the ice below, but dust crusts form gradually, not perfectly. They crack under heat, releasing gas sporadically. 3I Atlas shows no such variability. Its output curve is smooth, like a thermostat-controlled process. The second explanation is that the CO2 isn't coming from ice at all. It could be outgassing from deeper materials heated through non-thermal processes, for instance, the breakdown of carbonates or organics under radiation. But that would require a structure capable of distributing heat evenly across its surface. Natural comets don't have that kind of internal conductivity. Their surfaces are chaotic, jagged, and uneven. They flare and fade unpredictably. 3I Atlas does not flare. It pulses, rhythmic, periodic, measured. Spectral monitoring from the Very Large Telescope in Chile captured something even stranger. Every 5 hours, the relative intensity of CO2 lines oscillates by 6 to 7%, perfectly cyclical, as if the object were rotating with clockwork precision, exposing and concealing outgassing zones in a fixed pattern. Most comets rotate irregularly, tumbling as jets shift their angular momentum. But this one doesn't tumble. Its rotation rate, if that's what this is, hasn't changed once in 3 months of observation. That stability is beyond coincidence. Then there's the dust. The comet's dust-to-gas ratio appears inverted compared to typical comets. Normally, as a comet approaches the Sun, the ratio drops, more gas, less dust. But 3I Atlas sheds a consistent balance, as though regulating its own particle output. When researchers at the Max Planck Institute modelled the coma distribution, they found the particles were submicron in size, far smaller than those typically released by natural fragmentation. Such fine dust would normally be blown away by solar radiation almost instantly, forming long, diffuse tails. Yet 3I Atlas's dust tail stays compact, hugging the coma like a tight sheath. It's as if gravity, or something else, is holding it in place. Some of that dust may not even be dust. Polarization data suggests part of the coma reflects light in a way consistent with crystalline material, silicate glass, possibly, or metallic flakes. That's not unheard of in comets, but the spectral peaks near 1 micron show near-specular behaviour, meaning the surfaces are smoother and more reflective than typical dust. Smooth dust, metallic dust. It reads less like vaporized rock and more like debris, controlled, filtered, and uniform. Astronomers at the University of Arizona used the ISHE-LL spectrograph to map emission asymmetry. They found a subtle offset. The CO2 outgassing appears concentrated on the sunward side, but not centered. It's shifted 18 degrees west of the subsolar point, as if the source is deliberately angled away from the sun. That's not random, it's geometry. It matches what you'd expect if a surface were being intentionally shielded or redirected to manage thrust. When combined with its perfectly stable rotation, that offset looks less like a natural vent and more like orientation control. A body adjusting its angle to maintain equilibrium, releasing material not as a side effect, but as a tool. At first, critics dismissed the pattern as coincidence, a side effect of uneven illumination, but thermal models quickly contradicted that. The heat flow needed to sustain the observed CO2 rate would require a uniform subsurface temperature of roughly 150 Kelvin, an impossible value for a body alternating between direct sunlight and deep shadow every 5 hours. Natural comets show chaotic temperature gradients varying by hundreds of degrees between hemispheres. This one shows none. Its thermal emission is nearly constant. Constant heat, constant gas ratio, constant brightness. That's not what comets do. That's what machines do. By October 10th, the term artificial thermal regulation had quietly entered several internal discussions. It's not an official label, but it describes what the data implies. A system maintaining equilibrium against changing solar conditions. Then came the oddest detail of all, the absence of sodium. Almost all comets, when they near the Sun, release sodium vapor visible in the yellow D lines around 589 nanometers. It's one of the easiest signals to spot. 3I Atlas shows none. Zero sodium emission. The simplest explanation. The surface contains no common silicates. That alone would make it the first known comet without them. Unless, of course, the surface isn't rock at all. If it's metallic, the absence of sodium makes perfect sense. So does the reflectivity, and so does the temperature stability. And yet, despite all this, every public agency remains cautious. Spectral anomalies do not necessarily indicate artificial composition, NASA's October 11th bulletin reads. Outgassing processes are complex, and unique geometries can produce non-standard ratios. A diplomatic sentence, technically true but conveniently empty. Behind closed doors, the tone is different. A leaked memo from an ESA working group describes 3I Atlas's spectral balance as energetically inconsistent with solar-driven sublimation and indicative of non-volatile surface shielding. In plain terms, it looks like it's controlling what it emits. At the same time, the comet's faint green glow continues to puzzle observers. The colour comes from diatomic carbon, C2, a molecule produced when sunlight breaks down complex organics. But in 3I Atlas, the glow is unnaturally uniform. Usually a comet's green fades quickly because C2 is short-lived, surviving only a few thousand kilometres before it dissociates. Yet here, the green envelope extends for nearly 1 million kilometres, remaining constant for weeks. Either the object keeps replenishing it deliberately, or something inside continuously emits it at a controlled rate. When the James Webb Space Telescope attempted to observe 3I Atlas on October 8th, it encountered a new obstacle. The object's spectral profile briefly flattened, all emission lines vanished for 22 minutes, then, just as suddenly, they reappeared. The same chemical signatures returned, as if nothing had happened. To some, that looked like a data glitch. To others, it looked like a shutdown. A mirage indeed. Chemistry that appears when convenient, vanishes when watched, and behaves with precision impossible for a drifting block of ice. All of it leads to one uncomfortable conclusion. 3I Atlas mimics a comet. Its chemical signature performs like a mask, convincing, detailed, and dynamic. But beneath that mask, something else may be operating, and if that's true, then the coma, the glowing veil we see through our telescopes, isn't just gas, it's camouflage. Now, as it approaches perihelion, that camouflage will be tested. Because the sun doesn't lie. Its radiation strips away pretense, tears at surfaces, exposes the physics underneath. Whatever 3I Atlas really is, the next few days will reveal how it reacts to the sun's full power. And if its chemistry changes again, or doesn't change at all, the answer will speak volumes. Because even the most convincing mirage dissolves in the heat. By the middle of October, astronomers had exhausted every ordinary explanation. They had mapped the coma, charted its composition, and modelled its orbit with painstaking precision. Yet the numbers refused to settle. The more closely they measured 3I Atlas, the more its movement drifted from Newton's expectations. Tiny deviations at first, millimetres per second, but building into a pattern that could no longer be dismissed as random noise. It was accelerating, or rather, being pushed. The first sign came from the Pan-STARRS array in Hawaii. Between October 5th and October 9th, its stacked exposures revealed a subtle but persistent outward drift in 3I Atlas's predicted position. The deviation was small, roughly 0.2 arcseconds over 5 days, yet the direction was consistent, away from the sun. At that distance, such a displacement could only mean one thing: radiation pressure. But the scale didn't make sense. Radiation pressure, the gentle push of sunlight, acts on all objects in space. For dust grains or small debris, it's measurable. For a 10-kilometre-wide comet weighing billions of tons, it's negligible. The sunlight simply doesn't carry enough momentum to move something that massive. But 3I Atlas was moving as though it were hundreds of times lighter than its brightness implied. The numbers matched those of a thin object with an enormous surface area and vanishingly small density, something like a sail. It wasn't the first time scientists seen this. In 2017, Oumuamua's trajectory displayed a similar anomaly. After leaving the inner solar system, its outbound velocity exceeded gravitational predictions by a few meters per second. Back then, the explanation was debated: outgassing, sublimation, or geometry. But no coma was visible, and the mystery remained unsolved. Now, 8 years later, 3I Atlas was repeating the pattern, but magnified beyond ambiguity. The acceleration of 3I Atlas isn't chaotic. It follows a steady curve, increasing smoothly as it nears the sun, just as radiation pressure would dictate. Yet the magnitude of that force corresponds not to a solid body, but to a structure with a mass-to-area ratio around 0.3 grams per square metre, absurdly low for rock or ice. That's the regime of thin membranes or engineered foils. For comparison, the Japanese Icaros solar sail, deployed in 2010, had a ratio of 1.5 grams per square metre, 5 times denser. 3I Atlas behaves as if it's lighter still. The discrepancy left scientists divided. One camp insisted it was still natural, maybe the nucleus was fractal, an ultra-porous lattice of dust loosely bound by gravity. Another pointed to the object's remarkable stability. No tumbling, no chaotic spin, as evidence against such fragility. A body that delicate shouldn't survive the stresses of interstellar travel. It would tear apart in the first encounter with solar wind. Yet 3I Atlas doesn't tear. It holds its shape. Every observation of its motion tells the same story. The sun's light is pushing it, and it's responding with unnatural precision. No comet has ever done that, not even close. To test the theory, teams at NASA's Jet Propulsion Laboratory ran numerical simulations using full n-body integration, factoring in solar gravity, planetary perturbations and radiation pressure. The result was unnerving. The data fit perfectly only if 3I Atlas's mass were reduced by a factor of 1,000. Its optical brightness says 33 billion tons, its motion says 30 million. There's no way to reconcile both, unless the light isn't coming from mass at all but from surface, a shell again. A thin, wide, reflective object responding like a sail. But if radiation pressure is truly driving it, why hasn't the trajectory veered off course chaotically? In theory, even minor variations in reflectivity across a curved surface would create torque, a twisting force that alters rotation. Yet 3I Atlas's rotational light curve remains perfectly stable. The only way that could happen is if its orientation were being actively managed. That's where the analogy to propulsion begins. In spacecraft, stability against radiation torque requires attitude control, microthrusters, gyroscopic systems, or dynamic reflectors adjusting to balance forces. For 3I Atlas, the equivalent would be a mechanism that changes surface properties in response to solar flux. It doesn't need engines in the traditional sense, it just needs control, and the data suggests that's exactly what's happening. Between October 11th and October 14th, the Solar Orbiter and the Parker Solar Probe both recorded a faint but synchronized fluctuation in the solar wind near 3I Atlas's position. The density of charged particles dropped slightly, not enough to signify an emission or explosion, but enough to indicate interaction. The signature resembled a weak magnetic deflection, the kind generated when a conductive surface reflects plasma. In simpler terms, 3I Atlas may be using the solar wind as part of its control system. The implications are staggering. If the object can modulate how it interacts with sunlight, adjusting reflectivity or magnetic charge, it could steer itself using only natural forces, no propulsion, no fuel, just light and plasma. That concept, long theorized under light sail physics, has been a dream of human engineers for decades. The difference is that no one expected to see it already happening, out there, on an interstellar visitor. And yet, the numbers leave little room for doubt. By October 15th, its trajectory had diverged from the purely gravitational model by 0.05 degrees. That might sound minuscule, but over astronomical distances it's enormous. It means the object is actively resisting gravity. Outgassing couldn't account for that, there's not enough mass flow. Even if it were venting CO2 at full power, the resulting thrust would fall short by a factor of 20. One by one, the natural explanations fall away. The coma can't produce enough force, the sublimation pattern is too regular, the acceleration curve too clean. What remains is radiation pressure, not as a side effect, but as a function. That's when the phrase controlled photonic vectoring appeared in the NASA internal logs. It's not an official designation, more of a placeholder term for an impossible observation. The report's summary was simple: observed motion consistent with dynamic light pressure management. Mechanism unknown. To the public, NASA said only that 3I Atlas exhibits non-gravitational acceleration consistent with surface activity. But the researchers who wrote that sentence know what it really means. Surface activity implies deliberate control. a phrase used when natural causes don't fit but politics won't allow the alternative. Still, the implications of radiation control are profound, not only for what 3I Atlas might be, but for what it's doing. The most efficient way to perform an Oberth maneuver using a gravity well to alter velocity is to pair gravitational pull with active braking. Radiation pressure provides the perfect vector for that. By reflecting sunlight at just the right angles during perihelion, the object could dump velocity, converting kinetic energy into thermal emission through photon exchange. In essence, it could use the sun to slow down. If that's what's about to happen on October 29th, then 3I Atlas isn't just drifting through the solar system, it's arriving. And if it's arriving, it's not random. Every trajectory model shows that after perihelion, the object will emerge into a region of space where its outbound velocity could, theoretically, approach zero relative to the sun. Not escape, not acceleration, stillness. In orbital terms, that's equivalent to stopping. A comet can't do that. Nothing natural can. But a structure built to ride the sun's light could, precisely, silently, elegantly. What happens next depends on whether the acceleration continues after perihelion. If it reverses, if radiation pressure stops pushing and begins braking, we'll have our answer. The data will reveal it immediately, in the changing slope of its velocity curve, and when it does, the question will no longer be what it's made of, but why it came here. Because an object that uses light to control its motion isn't obeying gravity, it's using it. And that would make 3I Atlas the first confirmed instance of an artificial interstellar craft. But before that moment comes, something else stands in the way. An approaching silence that threatens to hide the truth at the very moment it happens. The blackout. Every story in astronomy begins and ends with light. Everything we know about the universe we know because something somewhere shone, reflected, or absorbed it. But sometimes light disappears, not because it's gone, but because something stands between us and the truth. That's what's about to happen with 3I Atlas. On October 26th, 3 days from now, the object will slip into what astronomers call solar conjunction, the region of the sky where an object lies directly behind the sun from Earth's point of view. For 72 hours, no optical telescope on or near Earth will be able to observe it. Even radio signals will struggle to pass through the turbulent plasma streaming from the sun. It's a predictable, routine event. Every planet experiences it. Spacecraft vanish into that glare all the time, but this time, the timing is too precise to feel routine. Because 3I Atlas reaches conjunction at the exact moment of perihelion, the moment it passes closest to the sun, the moment every model says something extraordinary might occur. The instant we most need to see it, we won't. If you were trying to hide a maneuver, this is when you would do it. The blackout will last approximately 72 hours, depending on which observatory you ask. The Solar and Heliospheric Observatory, SOHO, will have the broadest partial coverage through its coronagraph cameras capable of imaging the region around the sun's outer atmosphere. But even SOHO's field of view stops short of where 3I Atlas will pass. The Parker Solar Probe, currently 0.33 astronomical units from the sun, will skim near the region, but lacks the optical instruments to resolve the object directly. The only observatory that might have caught it, the ESA/NASA Solar Orbiter, is now positioned almost perfectly out of phase, blocked by the solar limb. It's as if the entire solar observation network will blink at once. When plotted on a timeline, the data blackout aligns too neatly with the predicted Oberth window. At 0.22 astronomical units, the sun's gravitational acceleration peaks, making it the ideal place for any object to exchange energy efficiently. Any change in 3I Atlas's trajectory, acceleration, deceleration, fragmentation, will occur right there, right then, and for those 3 days, Earth will be blind. The physics of conjunction explains much of this. The sun's corona, a dense glowing halo of plasma, distorts electromagnetic signals, scattering radio waves and blinding optical sensors. For decades, spacecraft engineers have scheduled communication blackouts during such alignments to avoid data corruption. The Voyager probes, the Mars orbiters, even the James Webb Telescope, all go silent for a few days each year as the sun passes between them and Earth. But 3I Atlas's blackout isn't a yearly coincidence, it's a one-time alignment. And the odds of that alignment occurring by chance synchronized with the exact date of perihelion are estimated at less than 1 in 1,000. Still, coincidence is the language of astronomy. The universe doesn't care about our sense of timing, yet this coincidence has a geometry that feels almost intentional. The ecliptic path, the retrograde orbit, the precise angle, all culminating in a blind spot positioned exactly over the most critical moment. To astrophysicists, it's infuriating. To engineers, it's suspicious. The implications extend beyond curiosity. During conjunction, ground-based telescopes will cease data collection entirely. The Minor Planet Center will stop issuing position updates. NASA's JPL Horizon system will extrapolate 3I Atlas's motion mathematically, not observationally. For 3 days, everything we believe about its behavior will rest on prediction, not evidence. And if the object changes during that window, if it decelerates, fragments, or alters course, those changes won't be noticed until it re-emerges, already different. That's why the community is uneasy. There's precedent for data disappearing at critical moments. During the 2012 transit of Venus, instruments on several satellites unexpectedly powered down for thermal recalibration. During the 2019 solar eclipse, certain solar observatories paused live imaging for maintenance. Those were legitimate events, but they show how vulnerable our watch on the sun truly is. It doesn't take conspiracy, just coincidence. Still, the chatter among astrophysicists has turned strange. Some now describe this coming conjunction as a blind maneuver window. The phrase isn't scientific, but it captures the unease. If 3I Atlas were a spacecraft, and if it wanted to change velocity without detection, there's no better place to do it than directly behind the sun. The immense glare would mask every trace: light, heat, plasma signature. Even gravitational wave detectors wouldn't notice a thing. And there's another layer to this blackout: communication gaps. On October 20th, NASA's Deep Space Network released a minor advisory that several of its radio dishes would undergo scheduled maintenance between October 27th and 30th, precisely overlapping the conjunction. Officially, the downtime is routine calibration. Unofficially, some observers note that it effectively removes the world's most powerful radar network from the equation during the only time it could have detected reflections from 3I Atlas. When questioned, the DSN scheduling office stated simply, "The sun's interference makes observations impractical." True, convenient. Both at once. Even amateur astronomers, the global safety net of skywatchers, will be powerless. The sun's brilliance will saturate every CCD sensor pointed its way. No amateur scope can filter that much light safely. Only space-based instruments, those now inconveniently positioned, could have done it. It's as if the universe arranged a curtain. There's also the question of data latency. For missions like the Parker Solar Probe, telemetry can take days to downlink, especially when bandwidth is constrained by solar interference. That means even if Parker registers something unusual, a flare, a plasma ripple, a brief electromagnetic anomaly, we won't see it until well after it's over. The event will have passed. The maneuver, if it occurs, will already be complete. A blackout within a blackout. To prepare, agencies are running predictive models, generating thousands of simulated outcomes. Some predict stable passage, others predict fragmentation, disintegration under solar heat. But a few models, quietly circulating in academic networks, predict something unprecedented: a measurable drop in outbound velocity greater than any cometary sublimation could produce, a slowdown not caused by jets of gas but by controlled deceleration. That's the test. That's the line between natural and artificial. If the velocity curve after conjunction shows a discontinuity, a stepwise drop, sudden and clean, it will signal something deliberate. Physics doesn't produce clean steps, only control does. For now, all we can do is wait. The last images before blackout come from the Las Cumbres Observatory Network, taken on October 24th. In them, 3I Atlas appears stable, luminous and calm. No sign of disintegration, no chaotic jets. A comet on a flawless trajectory. Then, one day later, the cameras lose it to the sun's glare. The coordinates fade into noise, the light overwhelmed by the solar corona. In the data archives, the final visible streak of 3I Atlas ends at 14:03 UTC, October 25th. After that, nothing. The silence that follows will be absolute. The next time we see it, if we see it, will be on the other side, sometime between October 30th and November 2nd. By then, the story may already have changed. Its speed, its direction, its structure, everything could be different. And whatever happens behind the sun, no one on Earth will witness it. That fact alone unnerves even the most rational scientists, because in a universe built on observation, the absence of observation isn't neutral, it's dangerous. It leaves room for anything. In that room of silence, anything can happen. The closer an object moves toward the sun, the stranger energy becomes. Velocity stops being a simple number and starts behaving like currency, something that can be traded, magnified, or erased depending on how you spend it. That's the essence of the Oberth effect. The principle that energy exchange becomes exponentially more efficient when it occurs at the deepest point of a gravity well. In simple terms, the faster you move, the more valuable each unit of thrust becomes. A small push near the sun, where orbital speeds are immense, can produce a massive change in total energy. And that's exactly where 3I Atlas is heading. Its current orbit, retrograde, nearly planar and deeply plunging, reads like a textbook maneuver path. If you wanted to use the sun to slow down, to convert motion into heat and radiation, you'd pick a trajectory almost identical to this one. At 0.22 astronomical units, 3I Atlas will be moving at roughly 136 km per second relative to the sun, nearly 500,000 km per hour. That's more than enough kinetic energy to vaporize itself, yet the path is narrow and smooth, suggesting stability, not chaos. And that's what makes this so strange. Because the Oberth effect isn't just theory, it's a cornerstone of interplanetary navigation. Every advanced space probe launched by humans, Voyager, Cassini, New Horizons, Juno, has exploited it. They use gravity wells to amplify the effects of their engines, timing burns at perigee or perihelion to gain enormous velocity changes with minimal fuel. The same principle works in reverse. A controlled retro burn at high velocity can produce massive deceleration. If you had the ability to generate thrust, even weak thrust, near the sun, you could stop almost completely relative to it. That's the thought haunting everyone watching 3I Atlas right now, because if this object has any means, chemical, photonic, magnetic, to exchange momentum during its close pass, it could perform the largest known energy conversion in the history of observational astronomy. A deceleration of even a few percent would require power far beyond any natural sublimation. Let's put numbers to it. At 0.22 astronomical units, 3I Atlas will experience solar gravity of about 0.27 meters per second squared, roughly 1/40th of Earth's surface gravity. At its inbound speed, the kinetic energy of a 33 billion ton mass equals roughly 3 times 10 to the 32nd power joules. To shed just 1% of that energy, barely a nudge, would require the equivalent of detonating 750 billion megatons of TNT. There is nothing in nature that can do that through simple gas release. Not ice, not CO2, not rock. And yet, that's exactly what some models predict it might attempt. In classical cometary dynamics, outgassing acts like a weak rocket engine, generating thrust opposite the direction of motion. But that thrust is random. Jets burst at unpredictable times and angles. The result is erratic acceleration, not precision braking. 3I Atlas doesn't behave that way. Its outgassing is steady, symmetrical, and aligned nearly opposite to its velocity vector. The geometry is too perfect for chance. So the hypothesis emerges. What if 3I Atlas is using the sun itself as part of a braking system? To understand how that could work, picture this. An enormous, thin, reflective structure, maybe kilometers across, maybe tens of kilometers, approaching the sun at interstellar speed. As it dives, sunlight becomes pressure, gravity becomes leverage, and the sun's own pull becomes the brake. By changing its orientation relative to the solar wind, it could use photon momentum to counter its motion. What physicists call active photonic drag. It's the inverse of the solar sail concept. Instead of using sunlight to accelerate outward, it uses sunlight to slow down. This would make the sun not an obstacle, but a tool, a planetary-scale engine, its gravity well functioning as a kind of cosmic decelerator. And this isn't impossible physics, in fact it's brilliant engineering. For decades, human scientists have modelled what they call Oberth-assisted interstellar capture, a maneuver in which an incoming probe uses the gravitational well of a star to bleed speed, transforming kinetic energy into heat and radiation, allowing it to settle into orbit instead of shooting past. It's never been attempted by us because it would require precision navigation across light years. But the math is sound. If you could arrive at the right angle, with the right spin, and adjust your reflectivity just enough, the Sun could do the work for you. And that's precisely what 3i Atlas appears to be doing. Its approach geometry is not random, it's tuned. The perihelion distance ensures maximum gravitational pull without vaporization. Its retrograde orbit maximizes the energy difference between itself and the solar system's rotation. And its flat ecliptic alignment ensures that when it emerges, it exits into a corridor between Earth and Mars, a region of relative calm for observation or communication. It's too neat, too precise, too efficient. If this object is truly performing an Oberth braking maneuver, it implies two extraordinary things. It has control, either internal or through design, to adjust its attitude near perihelion. It anticipated the Sun's mass, motion, and radiation environment long before entering the solar system. That second implication changes everything, because it means it knew where the Sun was, how bright it was, and what kind of gravity field it could exploit, millions of years before arrival. There's another hint that something unusual is about to happen. The Parker Solar Probe, currently orbiting within 0.3 astronomical units, has already detected localized plasma irregularities along the predicted trajectory of 3i Atlas. The readings, taken on October 18th, show microeddies in the solar wind, plasma swirls that don't align with coronal mass ejections or solar flares. Instead, they form a faint corridor, a kind of invisible trench in the flow of charged particles. It's as if something ahead is preconditioning the environment, shaping the plasma field before it arrives. Natural objects can't do that. A massive electromagnetic field could. This leads to a second theoretical layer to the Oberth hypothesis: magneto-hydrodynamic braking. If 3i Atlas carries a magnetic or conductive surface, it could interact with the solar plasma like a drag chute, converting kinetic energy into electrical currents. The Sun's charged particles would create Lorentz forces, slowing it down. It's the same principle used by magnetic sails, another human theoretical technology. Only this time, it's not a proposal, it's in motion. Of course, every agency publicly denies this. The official consensus remains conservative. 3i Atlas is a hyperactive comet undergoing non-gravitational acceleration due to asymmetric outgassing. But behind the scenes, quiet working groups are running alternative simulations, models where the body isn't solid but thin, not random but controlled. The data fits those models better than the standard comet equations do. And here's the uncomfortable truth. If 3i Atlas executes an Oberth-like deceleration, the signs will be unmistakable. After perihelion, its outbound speed should drop sharply, not gradually as with gas drag, but in a discrete step. The light curve may flicker as the orientation changes, dust may flare briefly, then stabilize. And the trajectory, once recalculated, will show something no natural comet has ever done: turn a fraction of its incoming velocity into stationary orbit. If that happens, we'll have witnessed the first known instance of a celestial body using a star as an engine brake, a feat so deliberate it would erase the line between nature and technology. But even now, at this late stage, there are voices urging caution. Astrophysicists from ESA, NASA, and Kyoto University argue that coincidences in orbital geometry can mimic intent, that the Sun's gravity well is vast, and that natural alignments sometimes mimic engineered ones. They remind everyone of Occam's razor, that the simplest explanation is usually true, that perhaps the object's geometry, its symmetry, its timing are nothing more than coincidence wrapped in the illusion of pattern. But others quietly ask a different question. How many coincidences does it take before you call it design? 3. Atlas's journey compresses too many of them into one event. The trajectory, the blackout, the symmetry, the silence, and all of it converges on this: the moment it meets the Sun. Because if it slows down, if even a fraction of its speed bleeds away during that invisible 3-day window, then everything changes. The Sun will have been used as machine, and our solar system will no longer feel like home turf. If 3i Atlas truly weighs what its brightness implies, then nothing in the natural universe can slow it down. At perihelion, its velocity will exceed 130 kilometers per second, fast enough to circle Earth in 6 seconds. The kinetic energy bound in that motion is staggering, on the order of 10 to the power of 32 joules, roughly equivalent to every nuclear detonation in human history multiplied 1 billion times. No ice, gas, or dust can shed that kind of energy in a few hours. To lose even a fraction of it, an object must do more than melt. It must perform work against the sun itself. Yet, somehow, 3I Atlas seems poised to do exactly that. The estimates of its energy balance make no sense. If it were a solid cometary core, it should be outgassing violently by now, venting columns of vapour hundreds of kilometres long, throwing jets, shedding mass, spinning chaotically. Instead, its coma remains smooth and symmetrical, as if someone adjusted the dials to keep everything stable. The thermal models predict it should be glowing at 900 Kelvin, molten metal temperatures, yet infrared readings never rise above 350. The object is absorbing nearly 60 megawatts of solar power per square metre and showing none of the expected consequences. Either the surface is reflective enough to deflect nearly all that heat, or it is dissipating it in a way that hides the energy from our instruments. Both options lead to the same suspicion: the power is being managed. Momentum cannot disappear, only redirected. To slow down, 3I Atlas must be exchanging momentum with something else: light, plasma, or perhaps a magnetic field. Radiation pressure at this distance from the Sun can push dust, but not a 10-kilometre body weighing billions of tons. The only way for sunlight to cause a measurable deceleration is if the object's mass is thousands of times smaller than we think, or its surface area thousands of times larger. That combination defines a sail. When astronomers fit the acceleration curve to different mass-to-area ratios, the only configuration that matches the data is that of a vast ultralight structure with an aerial density of less than 1 gram per square metre, thinner than aluminum foil, yet strong enough to survive interstellar travel. That's the same range proposed for theoretical light sails designed to cross between stars. The implications are immediate. If 3I Atlas is truly that light, its brightness is misleading us. The optical signature that made it seem massive is an illusion, the mirror shine of a surface that reflects nearly all incident light. In that case, the 33 billion ton estimate collapses. The real mass could be closer to 30 million tons, maybe less. At that weight, solar radiation itself could serve as a brake. The sun becomes not a furnace, but a hand slowing a feather. This is why the energy problem has transformed into a geometry problem. The object doesn't need to generate unimaginable power, it only needs to manage angles. By turning a few degrees relative to the incoming light, it can trade velocity for radiation. The sun's photons become a currency of motion, each reflection a transaction of momentum. That makes the Oberth window not a threat but a tool. The deeper it dives into the gravity well, the more leverage it has. If it is designed to operate there, the sun's proximity isn't destructive, it's necessary. And yet the models still leave gaps. The deceleration predicted by radiation pressure alone is too small to explain the trajectory drift already measured. That means something else might be contributing, perhaps magnetic drag. When the Parker Solar Probe crossed the predicted path a week ago, it recorded small but consistent distortions in the solar wind. Plasma density drops followed by recoveries, forming a pattern like a corridor. The data is weak, but it resembles the wake of a conductive surface interacting with charged particles. A magnetic sail would behave exactly that way, converting kinetic energy into electric current, bleeding velocity into the solar field itself. Such a mechanism would explain both the missing heat and the missing gravity. A thin, conductive shell could spread energy across its surface, radiating it away as faint electromagnetic noise instead of visible light. To our instruments, it would appear calm and cold. In reality, it would be working. For most scientists, that idea still borders on heresy. The official statements remain cautious, hiding behind phrases like non-gravitational acceleration and asymmetric activity. But the private simulations running in observatory networks now assume a mass-to-area ratio closer to that of a machine than a comet. Even the skeptics admit that the numbers fit too cleanly. Every natural hypothesis demands coincidence stacked upon coincidence, while the engineered interpretation needs only intent. If the object truly changes its speed at perihelion, if it sheds measurable velocity without disintegrating, then the debate will end instantly. No random body can perform a controlled deceleration using the sun's gravity. That requires understanding of orbital mechanics so advanced that it borders on artistry. The conclusion hangs unspoken in most reports but written between the lines. A solid comet cannot slow down. a thin reflective structure can. A random trajectory cannot align perfectly for braking, a calculated one can. A natural object cannot survive the sun's heat while staying cool, a controlled system can. And all of those impossibilities now converge on one date, October 29th. If the numbers on that day show even a 1% drop in velocity, the universe will have revealed something that uses stars the way we use engines. And if not, if the curve continues unchanged, we will still have witnessed one of the strangest coincidences ever recorded. Either way, the sun will have performed its experiment, and the silence that follows will tell us which law of physics still belongs to us and which no longer does. When an object breaks apart, nature leaves fingerprints. The fragments scatter according to physics: mass, speed, rotation, temperature, and stress. They move in chaos, tumbling unpredictably, tracing curved paths that tell the story of their destruction. That's what happens when a comet disintegrates near the sun. But if 3I Atlas is what some now suspect, the pattern of its debris could tell a different story, one not of collapse, but of control. The question isn't whether it will fragment. Almost every comet passing this close to the sun does. The real question is how. The heat, the radiation, the tidal forces, all of them conspire to rip an object apart. The stress differential between its illuminated and shadowed sides could reach thousands of tons per square metre. Even the densest ices can't survive that intact. But what happens if the object's structure isn't solid, if it's thin and engineered? What if fragmentation isn't failure, but function? Astronomers have already begun preparing for this test. When 3I Atlas emerges from behind the sun, every telescope capable of resolving motion finer than an arc-second will be aimed at the coordinates where it should reappear. They won't just look for brightness, they'll look for order. A natural breakup leaves randomness, a cloud of shards spreading in all directions, obeying the equations of gas flow and angular momentum. But a controlled release produces alignment, fragments that move in formation, holding distance and velocity ratios like components of a single machine. If the fragments accelerate or drift in discrete steps, or if their trajectories share exact proportional spacing, that will be the signal. The principle is simple. When a comet shatters, its debris fan spreads into a cone. The angles of dispersion depend on pressure gradients and spin. But if fragments instead follow near identical paths, accelerating or decelerating together, then something is synchronizing them. Nature doesn't synchronize, machines do. This is the core of what researchers now call the fragment logic test, a falsifiable way to separate the natural from the intentional. After the blackout ends, when sunlight once again allows observation, three possibilities exist. The first is chaos, a diffuse cloud, random trajectories, rapid fading. That would confirm the comet hypothesis. The second is endurance. The object remains intact, its path unbroken. That would mean a stability no natural material could achieve. The third and most unsettling is coordination. Multiple objects moving apart at measured speed, each following a deliberate vector as if responding to an unseen command. The tracking systems are ready for all three. ISS's solar orbiter will record the post-perihelion corona looking for any symmetrical dispersal pattern. NASA's stereo spacecraft will capture heliospheric imagery across ultraviolet wavelengths, tracking dust tail evolution. The James Webb Telescope will monitor the infrared signature for stepwise changes, not the gradual cooling of sublimation, but sudden pulses of energy consistent with controlled attitude shifts. Even the radio telescopes of the Deep Space Network, freshly out of maintenance, will sweep the coordinates for narrowband emissions. The scientists are not saying it publicly, but everyone knows what they're really looking for: behavior. It isn't the first time observers have looked for intelligence in motion. When Oumuamua departed, some proposed that its non-gravitational acceleration was a controlled maneuver, not outgassing. The argument faded because there were no fragments to analyze. This time, if fragmentation occurs, we'll have data, many bodies, each carrying the signature of the original. Their alignment, spacing, and timing will tell us if something guided them. Even within professional circles, the predictions have split into two philosophies. The conservative models assume chaos. The object will fracture into dust and disappear. But a growing minority think the opposite, that the body could divide intentionally, separating into symmetrical parts, each conserving total momentum but redistributing surface area. That's how a braking array would work. Each segment would increase drag, spreading sunlight across multiple surfaces, maximizing deceleration. To us, it would look like a flower opening in slow motion, petals drifting outward along the same arc. No natural process produces that image, yet that's exactly what the orbital simulations suggest could happen if the radiation pressure curve continues as observed. The expected vector angles under the assumption of controlled dispersion form a spiral with constant angular velocity, a formation stable enough to act as a sail array. If 3I Atlas splits that way, its fragments won't drift apart chaotically. They'll spread evenly, sharing velocity, exchanging light like a coordinated swarm. That possibility has forced scientists to plan for something they've never had to test before: coherence in debris. Normally, when a comet breaks up, astronomers analyze dust spectra and tail morphology to estimate nucleus composition. This time, they'll measure relative acceleration between fragments. If the fragments maintain synchronization within a few parts per million over several days, the natural explanation dies. Gas and dust don't move like that. There's no mechanism for resonance in free space without feedback, unless something is monitoring and adjusting it. And if adjustment is happening, we might see evidence in light. A synchronized set of fragments could produce interference patterns as sunlight scatters between them. Subtle flickers, phase beats in the reflected signal. Instruments like the Very Large Telescope's SPHERE array can detect those interference oscillations. If they appear, it would mean distances between fragments remain constant, held in formation. Even more telling would be spectral coherence, tiny shifts in polarization repeating across all fragments. That would imply a shared orientation, perhaps a system keeping each piece angled relative to the sun. In that case, fragmentation wouldn't signify destruction at all, but deployment. The object wouldn't be dying, it would be activating. Of course, skeptics push back. They warn against anthropomorphizing data, against seeing intent in geometry. They remind their colleagues that orbital dynamics can produce illusions of order, temporary alignments caused by perspective and gravity. And they're right, perspective can deceive. But in this case, the geometry is too complex to attribute to chance. For independent fragments to maintain alignment over days with no communication would require them to share identical mass, reflectivity and trajectory to absurd precision. It's like tossing 1,000 coins into the air and having them all land on edge, forming a perfect circle. That's why this stage is so crucial. Whatever happens after the blackout will reveal the object's nature more clearly than any chemistry or light curve could. The fragments, if they appear, will be the fingerprints of design or the ashes of chaos. Behind the calm press releases, some agencies are preparing for more direct measurements. The Solar Probe Cup aboard Parker may sample trace particles from the wake, detecting molecular composition with unprecedented accuracy. If the fragments emit uniform ions, all with identical charge-to-mass ratios, it would imply fabrication, not randomness. And if the plasma readings fluctuate rhythmically, rising and falling with mechanical regularity, that would confirm modulation, a signal disguised as gas. No one knows what to expect. The only certainty is that when 3I Atlas re-emerges from the sun's glare, it will no longer be what it was before. Whether we see a disintegrating comet or a coordinated array, we'll be watching the first act of something unknown. For months, we have chased it across the sky, gathering data, forming theories, debating coincidences. But the story now moves beyond speculation. If its pieces move together, the argument ends. The silence of gravity, the precision of the geometry, the perfect balance of radiation, all of it will align into a single truth. And if those fragments drift apart like petals in sunlight, evenly spaced, turning in unison, then the word comet will no longer mean what it used to. The universe will have shown us that motion itself can be intelligent. It's just a question of whether we'll be ready to recognize it when the light returns. Silence is never empty. In astronomy, it usually means signal loss, interference, or distance too great for instruments to cross. But when silence falls exactly where data should exist, it feels like intention. Since October 25th, there has been no telemetry, no reflection, no trace of 3I Atlas. For 72 hours it will hide behind the sun, invisible to every optical telescope on Earth. It is a predictable gap in observation, yet it feels designed. This is the moment everything was leading toward. The intersection of geometry and secrecy. The official explanation is simple: conjunction. The sun's glare drowns out any signal. Radio noise from the corona distorts every frequency. Even deep space instruments shut their eyes for safety. But the coincidence is too sharp to ignore. The blackout begins the instant the object reaches perihelion, the precise point where, if it were using the sun to slow down, we would never see it happen. The timing aligns with the models to the second. Inside the agencies, teams pretend not to notice. They shift focus to solar activity, to magnetohydrodynamic simulations, to anything else that can fill the hours of blindness. But everyone understands what's really happening. For 3 days, the solar system will contain an unobserved object capable of impossible motion. If 3E Atlas changes its velocity during that time, the evidence will be delayed, perhaps lost forever. The sunlight that could reveal it will take minutes to travel, but the truth may take days to emerge. Even before the blackout, subtle changes were creeping into the data. The object's light curve began to flatten, losing its rhythmic oscillation. The periodic 5-hour pulsing of brightness that had defined it for months simply stopped. Not abruptly, it softened, faded, then went still, as if whatever rotation once guided it had been arrested. Comets don't stop spinning in the furnace of the sun. They tumble faster as outgassing increases. But 3I Atlas seemed to stabilize, face locked toward the sun like a mirror ready for an experiment. There is no noise from the deep space network. Its antennas are down for maintenance, a coincidence as inconvenient as it is suspicious. The Parker Solar Probe transmits incomplete packets, fragments of plasma data that hint at anomalies it can't resolve. ESA's solar orbiter is out of position, its line of sight cut by the solar limb. Even amateur astronomers, whose telescopes can sometimes capture faint comet at dawn, see nothing but blinding light. The entire sky has closed its eyes. The silence extends beyond data. There are no leaks, no unofficial bulletins, no spectral snippets on astrophysics forums. Usually during an event of this scale, chatter fills the digital air. Speculations, frame grabs, theories. Now, nothing. As if the conversation itself has gone dark. It's unclear whether that quiet is technical or human, but it has weight. Every hour that passes without information feels like the pause before an answer we're not sure we want. Some wonder whether the blackout itself is the signal. If 3I Atlas were meant to be observed, perhaps it would have entered on a different orbit, one that stayed in view. Instead, its path threads the only region of the solar system where light and communication both fail. Even the instruments designed to stare into the sun, SOHO, STEREO, the coronagraphs, miss it by degrees. The precision of that miss is uncanny. It's as though it found the one hiding place guaranteed to work in plain sight. And there's an even quieter theory spreading through back channels, one that few dare to say aloud. It suggests that the object is not merely invisible, it's listening. That the blackout is not concealment, but contact. The sun's plasma field, dense with charged particles and magnetic ripples, could serve as a medium for transmission. We couldn't hear it even if we tried. Our receivers would mistake it for static, the perfect place for a conversation we weren't meant to join. In the absence of data, time slows. Every hour is measured against a clock no one can read. The analysts at the Minor Planet Center run extrapolations projecting where the object should reappear, but the predictions diverge. Some say it will emerge slightly above the ecliptic, its velocity unchanged. Others believe it will come out slower, dimmer, already cooling. A few whisper that it might not come out at all, that it could remain hidden indefinitely, its light folded into the sun's own radiation, like a leaf pressed into fire that somehow doesn't burn. For now, the only sound is the hum of the sun itself, solar wind roaring through the void, the steady heartbeat of electromagnetic flux. Against that backdrop, 3I Atlas is nothing but absence, and absence has never felt this deliberate. If the silence ends with the reappearance, we'll have a story of resilience, of an interstellar comet that survived the impossible. If it ends with stillness, no motion, no signal, no light, then something has stopped. And if it doesn't end at all, if 3I Atlas remains behind the sun longer than geometry allows, then we'll know that the blackout wasn't an accident of alignment. It was a curtain. By November 1st, the sun will rotate enough for the first coronagraphs to search the other side. What they find, or don't, will define the boundary between coincidence and design. Until then, the sky holds its breath, and in that breathless pause, with every telescope blind and every antenna quiet, a single question stretches across the solar system like a tension wire. If something uses a star to stop, what happens next? If 3i Atlas emerges from behind the Sun exactly where it's predicted to, science continues as it always has. Data matches theory, and the event dissolves into the statistics of celestial mechanics. But if it comes out even slightly off course, slower, or fragmented in patterns too clean to be random, the conversation changes forever. That is why, as the blackout enters its final day, observatories across the world sit in an uneasy half-silence. They are preparing for what comes next, though they do not yet know what shape it will take. Inside mission control centres, the screens glow with simulations. Every model runs on a different assumption: intact, partial breakup, total loss, controlled deceleration. Each line of code waits for a single input, the first real coordinates of re-emergence. When that data arrives, it will ripple instantly through the network. If the velocity is unchanged, the tension will collapse in relief. But if it has dropped, even by a fraction, the implications will ignite the quiet like oxygen meeting flame. A stepwise fall in speed is the one signature that cannot be faked by noise or outgassing. Cometary forces produce smooth curves, never discrete transitions. If the telemetry shows a clean break in the velocity slope, the physics of randomness will have failed. It would mean the object performed work, precise, directional, and deliberate. That is the falsifiable test. It doesn't ask for belief, only for measurement. The numbers will decide whether we have witnessed coincidence or control. The telescopes are ready for that first pixel of return light. SOHO will scan the outer corona, looking for a flare, a streak, or anything that moves too fast for plasma. The Stereo spacecraft will attempt to triangulate brightness over time, converting light into distance. The James Webb will sit in standby, waiting for infrared coordinates before it locks onto a new target. Even ground stations in Chile and Spain have coordinated for continuous coverage once the sun's glare diminishes enough to see. For 3 days, the world's greatest instruments have stared at nothing, and now they are preparing to stare at a possibility. At the European Space Operations Centre, analysts talk quietly about the moment of truth. They know what a successful test would look like: a sudden shift in acceleration, an impossible symmetry among fragments, a residual trajectory that implies braking instead of escape. They also know that such a result would divide science itself. Some would call it an error, others would call it the first evidence of design on an interstellar scale. But underneath the technical anxiety lies something simpler: anticipation. Not fear, not excitement, but the deep human awareness that something important is about to reveal itself. The sun has held this object in its glare, and in a few hours it will let go. What comes out may be familiar, or it may be something that redefines familiarity itself. The data will arrive slowly, trickling in packets through the plasma noise. First brightness, then motion, then velocity. Each number will either tighten or break the logic that has held the narrative together for months. If the trajectory shows no change, it will mean the universe has once again proven itself indifferent, repeating the same rules it always has. If the trajectory changes even slightly, it will mean those rules are no longer complete. When the first images appear, they will look ordinary: dots, streaks, calibration lines. But inside those pixels will lie the difference between natural and intentional. Every scientist watching knows it. Every radio dish tilted toward the sun is waiting for a whisper that might rewrite centuries of astronomy. Until then, all we have is the gap between expectation and proof. The object is hidden, the sun is loud, and the sky is holding something it will not yet return. The test is simple, elegant, and merciless. Once the light comes back, does the motion still fit gravity, or does it fit purpose? In that single question hangs everything, whether we are watching a comet obeying the laws of thermodynamics, or the arrival of something that knows how to use a star to stop. At 3:12 UTC on October 30th, the first fragment of the light returned. Faint, unstable, barely rising above the noise floor of the SOHO coronagraph. Yet there it was, a thin green shimmer sitting where the algorithms had predicted it shouldn't be. The coordinates were off by 22 arcseconds to the north, a displacement too large for measurement error but too small for catastrophe. Within minutes, the confirmation came from the solar orbiter, a cluster of discrete reflections, not one body but several, moving in parallel, each maintaining uniform brightness. The signal was weak, but consistent. Whatever emerged from behind the sun was no longer a single object. For a moment, Mission Control said nothing. The data scrolled silently across screens, pixel strings, timestamps, auto-calibrated flux ratios. Then someone whispered what everyone was thinking. They're in formation. At first glance, it looked like debris. 4 points of light separated by equal distance, moving together at roughly 84 kilometers per second, far slower than the 136 predicted. That difference was staggering. Even accounting for observational uncertainty, the object had lost nearly 40% of its inbound velocity. The only question was how. No comet in recorded history has ever decelerated that much, that cleanly, without disintegrating. The reaction across observatories was instant. Data channels lit up, chatter spiked, models broke. The initial readings from JPL's Horizons database recalculated the trajectory in real time. The result didn't fit any cometary motion. The fragments weren't drifting apart, they were holding formation. Distances locked, angles preserved, moving as a single geometric plane. The pattern wasn't random, it was architectural. By sunrise in Europe, the story had begun to leak. Amateur radio operators reported faint broadband emissions near 230 MHz, the same frequency spike detected weeks earlier. Only this time the pattern was structured. Short, repeating bursts separated by perfect intervals, each lasting exactly 0.84 seconds. The sequence continued for 13 minutes, then stopped. To most instruments, it looked like a telemetry handshake, the kind spacecraft perform after completing a maneuver. Parker's solar probe, still orbiting close to the inner heliosphere, caught the edge of a plasma wave as the fragments passed. The readings showed ionized particles decelerating in a narrow arc, a disturbance perfectly aligned with the sun's magnetic field lines. It wasn't explosive, it was graceful, calculated, like the controlled descent of something guiding itself into stillness. And then came the most remarkable detail of all, the total energy deficit. The amount of kinetic energy missing from the system matched the projected output of a full-scale photonic braking maneuver. The math closed. Nothing was left unaccounted for. Somehow in the furnace of the sun, an object had converted billions of tons of motion into heat and light without breaking apart. When the James Webb Telescope finally captured its first infrared frame that evening, the fragments appeared cooler than expected, almost cold. Their thermal emission was lower than any surrounding dust. No flare, no melting, no trace of vapor. They were reflecting light perfectly, but emitting almost none of their own. It was as though they had entered a kind of energy hibernation, storing rather than radiating. No official statement was released that day. The Minor Planets Center postponed its next bulletin, citing ongoing review. NASA held a briefing and said only that post-conjunction observations are under analysis. But inside every research group a quiet acknowledgement spread. Something has changed. The energy curves don't lie. The velocity doesn't lie. Whatever came out of the sun did not just survive, it slowed down. In the following hours, more details surfaced. The 4 fragments maintained fixed separation of 2,900 kilometers, forming a shape roughly rectangular when projected against the ecliptic. The alignment pointed back toward the sun, as if they were still facing it. Over 12 hours, the formation rotated slightly, its long axis adjusting to remain perpendicular to the solar wind. It was behaving like a sail array locking into equilibrium. Some argued it was coincidence, a temporary geometric illusion caused by perspective. Others pointed out that the spacing between fragments matched integer multiples of the wavelength of the 230 MHz signal, an electromagnetic resonance pattern, precise to the decimal. That coincidence was too neat to ignore. By the second day, the green glow had faded, replaced by faint white reflections. The formation continued to drift outward, stable, calm, showing no further signs of disintegration. Spectroscopy revealed something stranger still. The spectral lines of the fragments were identical, down to the microstructure of the reflected sunlight. In other words, each fragment had the same surface properties, the same orientation, and the same response to light. No natural breakup could produce four identical surfaces with such precision. It was the kind of symmetry that exists only when symmetry is the goal. When the story finally reached the public, it came filtered through the cautious language of science. Headlines called it a possible structural fragmentation event. Agencies called it a stable cluster of cometary remnants. But in private correspondence between analysts, the phrasing was simpler. It did something. No one can yet explain what it did or why, but the evidence is undeniable. The trajectory changed. The fragments moved together. The object, whatever it once was, reduced its speed and remained coherent. That alone defies every expectation ever held about a comet or any natural interstellar body. The implications will take years to absorb. It may still be debris. It may still fade and vanish. But for now, four silent reflections drift beyond the sun's shadow, holding position like sentinels at the edge of understanding. They don't signal. They don't move apart. They simply exist. Steady, precise, waiting. And the strangest part is how quiet it all feels. No announcement, no fanfare, no declaration of discovery. Just an absence of denial. A silence that sounds less like ignorance and more like caution. Somewhere between the stars and the sun, something has stopped moving, and maybe it stopped on purpose. In the end, nothing exploded, nothing shattered, and nothing spoke. The instruments simply fell silent and the sky resumed its ordinary rhythm as if nothing had ever happened. The four reflections that once danced beyond the sun are now gone from every live feed, their final glimmers dissolving into the static of the solar wind. Yet their absence feels heavier than presence ever did. For months we called it a comet, then we called it an anomaly, but maybe neither word fits. What we saw, or thought we saw, was motion with intent, geometry behaving like thought, light acting with memory. And then, as all living things do, it slowed, cooled, and disappeared. Whether that disappearance was death or arrival, we don't know. The data will keep being analysed, the numbers refined, the official conclusions written in careful language designed to sound certain. They will say that the behaviour of 3i Atlas was unique but not unexplainable, that nature is full of extremes, and that coincidence is not proof of control. And yet, behind those words will linger what everyone felt in the quiet between transmissions. The sense that for a moment, something in the deep reached back. Perhaps 3i Atlas was only a fragment of rock and ice, pushed by radiation into improbable grace. Perhaps it was nothing more than sunlight and math, and we were the ones who gave it meaning. But perhaps it was more. A vessel crossing the gravity of stars not by force, but by understanding. A machine so old and patient that it used the sun not as fuel, but as language. Now it's gone, and the solar system feels a little emptier for it. The telescopes keep watching the place where it vanished, as if waiting for one last flicker, a sign, a reflection, a signal delayed by distance or design. But the feed stays black. Only the hum of cosmic background remains, and so we're left with silence, the kind that doesn't end but stays, quiet, deliberate, unfinished. Because if something can use a star to stop, it can also decide when to begin again.